In this video we'll talk about binary search tree, insertion. So in binary search tree we all the elements, so you have root, all the elements on the left side of the root node will be less than the root, and all the elements on the right side of the root will be greater than or equal to root. So this is the condition which we have to follow. Let us understand the logic behind how to create a binary search tree by an example. So assume that so these are the given set of elements for which we have to create a binary search tree. First, element 5. So initially the tree is empty, so element 5 will be inserted and 5 will be your root node. Next, element 4 has to be inserted. So every time we check this condition, we always start from the root. So 4 is less than 5. So we say that all the elements which are less than the root or the parent node should be on the left side of the root or the parent node. So here 4 is less than 5, so and on the left hand side we don't have any other nodes, so directly element 4 will be inserted here. So next element you have is 3. Again you start with this condition, 3 is less than 5 and also 3 is less than 4. Same condition, so you have 1, so 1 is less than 5 and 1 is less than 4 and 1 is less than 3. Okay, so 1 will be placed here. Let us assume that this is element 12. Okay, so you have element 12, so 12 is greater than 5, so 12 will be coming onto the right hand side. Next you have is element 6. 6 is greater than 5, you come to the right hand side, you have an element here, and 6 is less than 12. So you have minus 1 is less than 5, come to the left hand side, minus 1 is less than 4, come to the left hand side, minus 1 is less than 3, minus 1 is less than 1, so minus 1 will be placed here. Next you have is 11. 11 is greater than 5, you come to the right hand side. 11 is less than 12, you come to the left hand side, and 11 is greater than 6, so 11 will be placed here. So this is a binary search tree for you. Let us take another example. So first node is 11, so 11 will be the root node for you. Next you have element 12, so 12 is greater than 11, so 12 comes on to the right hand side. Next you have element 5. 5 is less than 11, so 5 will be placed on to the left hand side. Next you have 6. 6 is less than 5 and 6 is greater than 5, so 6 comes on to the right hand side. Next you have 7. 7 is less than 5, but 7 is greater than 7 is less than 11, so comes to the left hand side. 7 is greater than 5, come to the right hand side, and also 7 is greater than 6, so 7 will be placed onto the right hand side. You have 9. 9 is less than 11, 9 is greater than 5, 9 is greater than 6, 9 is greater than 7, so 9 will be placed to the right side of 7. Next you have is 14. So 14 is greater than 11, you come to the right hand side, and also 14 is greater than 12, so 14 is placed here, and the rest of the nodes are null nodes for you. So these are null nodes. So this is a binary search tree for given set of elements. Okay, so let us take another example. Let us take So let us have the first element, which is 13, which is root, Next you have is 14. 14 is greater than 13, so 14 comes down to the right hand side. Next you have 7. 7 is less than 13, so 7 comes down to the left hand side. Next you have is 3. So 3 is less than 13 and 3 is less than 7, you come to the left hand side. Next you have is 27. 27 is greater than 13, you come to the right hand side. 27 is greater than 14, you have come to the right hand side of it. Next you have is 28. So 28 is greater than 13, 28 is greater than 14, and 28 is greater than 27, so you come to there. Next you have is 3. So now 3 is already inserted for us, let us ignore this. Next you have is 2. 2 is less than 13, 2 is less than 6, and 2 is less than 3. Let us assume we want to insert an element called as 5. 5 is less than 13, 5 is less than 7, but 5 is greater than 3, so 5 is available here. So sorry, this is element 2. Next, let us assume you want to insert an element called as 11. So 11 is less than 13 and 11 is greater than 7. Next, you want to insert, so this is your given binary search tree which you have built for the list of elements. So what are the advantages of what is the advantage of having this binary search tree is, if you move towards the left hand side, the leftmost element will be your minimum element in the given set of elements. If you move towards the right hand side, so the rightmost element will be the maximum element in your given set of elements. So here the minimum element is 2 and here the maximum element is 28 for you in the given set of elements. So why is this important is here suppose the main reason behind organizing the data in the form of binary search tree is to reduce the time taken. So the main reason for organizing the data in the form of binary search tree is to reduce the time taken. So time taken to search an element, to search, that is number of comparisons to find an element should be reduced. So here we do that because assume that this is an array. If all the elements are stored in an array, how many comparisons does it take to find the maximum element in this list? So here first you check 13 is greater than, so assume, so the logic which we use to find a maximum element is, you assume that 13 is the maximum element, that is first element is the max. You check whether 13 is greater than 14. If 13 is not greater than 14, this becomes your maximum element. Then you check 14 is greater than 7. Yes, 14 is greater than 7. Then you check 14 is greater than 3. Yes, 14 is greater than 3. Then you check 14 is greater than 27. No. So now what will happen is this becomes, to till here how many comparisons happened? 1, 2, 3, 4 comparisons have been done. Again you check 27 is greater than 28. No. So 28 becomes the maximum element, so 5 comparisons. Next again you check 25 is greater than 2. No. So 6 comparisons. 25 is greater than 5. No. 7 comparisons. 27 is greater than 11. 8. So you had total of 8 comparisons. So how many elements did you have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So if you had 9 elements, so you required 8 comparisons to tell whether to find the maximum element in an array. The same logic applies for minimum element. So also you require 8 comparisons for finding minimum element. So if the size is n, you require n minus 1 comparisons for finding max and also n minus 1 comparisons for finding the minimum element. So but here let us see how many comparisons do you require. So what you do is you move towards the left. So to find the minimum element, you move towards the leftmost. So the same list, if it is organized in the form of binary search tree, and if you want to find the minimum element in that, you move towards the leftmost side of the binary search tree. So let us see how many traverses, how many elements do you have to come across to reach the leftmost element. So one element, so first element you have come across, second element and third element. So at third element you have found out, that is at each and every element you have to check if there is a left node, you move towards the left node. If you don't have a left node, you stop there. That is your leftmost element. So logic for finding minimum is, you start at the first is, you start at root, then you check if left node is available. Then what you do is, then move to left node, otherwise else return the node. So this is the logic for finding the minimum element in the list. That is, now according to this logic, you start from the node. If you have a node, that is one comparison, so you move toward that. Yes, I have a node, I move towards the element 7, so one comparison here. Again I check at node 7, I have a left node. Yes, I have a left node, I move towards the left hand side, second comparison. Again at this point I check if I have a left node or not. Yes, I have a left node, I move towards the left hand side, third comparison. Then again I check, do I have a left node? No, I don't have a left node. If I don't have a left node, what do? I return the node. So 2 gets returned, which is a minimum node. So how many comparisons did I require? So finding the minimum element, I required 3 comparisons. So but here how many comparisons do I require? I require 8 comparisons for finding an element. Similarly for finding the max element, the same thing. If you, so this point will be replaced with if right node. If you have a right node, you move towards it. If you don't have a right node, then you, so this will also be renamed as right node. If you have a right node, you move towards it, otherwise you return the node. So if you want to find the maximum element, same thing. So I have a right node, I move towards it, one comparison. I have a, for this node I have a right node, I move towards it, second comparison. For this node I have a right node, so I move towards it, third comparison. So for this node I don't have a right node, so what do? I return the node. So here also required 3 comparisons. So for finding the maximum element also I required 3 comparisons. So in the small set of elements itself, I can see that searching becomes easier for me. That is, time taken for searching an element, that is number of comparisons are reduced for me when I am searching for an element. There is also another advantage for studying, another motivation for studying about BST, that is sorting. So without much effort, sorting can also be applied for us. And also one thing, other advantage which you have is searching. Okay, so let us see how sorting and searching becomes easier once you store the data in this form, that is in the form of binary search tree. How sorting, so one thing is, obviously searching is easier, that is finding the minimum, finding the min and max is, finding min and max becomes easier. How do you search? Searching and sorting also becomes easier for us. So for example, consider this binary search tree. So this is your root. So logic for searching is, first condition is, if node equal to the element which you want to search, then you return the node. Then otherwise what you check is, you check whether if node is less than the element, move to the left, and again you start from point number 1. Third is else if node is greater than or equal to the element. Okay, or you can, the element is, or you can check that element, if it is element is if element is less than node, you move towards left. If element is greater than or equal to the node, you move towards right. So you say that move right, and again you start at step 1. So if you follow this, and if you want to search for an element called as 11, so according to our algorithm, you start from the root node, you check whether 11 is equal to 5. No, 11 is not equal to 5. You come to the else if statement. In your else if statement, you check whether the element is greater than 5 or less than 5. So here the element is greater than 5. So if element is greater than 5, so what you do is you move towards the right hand side. So you come towards the right hand side. Then what do you do? Again you start from the first point onwards. Again what do you do is, again all the 3 instructions has to be executed. Again you check, that is whether 11 is equal to 9. No. Is 11 less than 9 or greater than 9? So 11 is not less than 9 and 11 is greater than 9. So what you do is you move towards the right. You are at this point. Then again you start from the first element. Node is equal to element, yes. So what you do is you return the element. So element 11 gets returned. So with only 3, so in a set of 7 elements, in 3 comparisons only you can find the element 11. Okay. Similarly, if you want to find element called as 4, the same steps, you check whether 4 is equal to 5. No. Whether the element which you are searching is the current element. No. Then what do you do is, if this is not the case, then you move towards, you check whether 4 is less than 5 or greater than 5. 4 is obviously, element 4 is less than 5. So obviously what it is, you move towards the left hand side, and again you start from the first point onwards. Again you check whether 4 is equal to 3. No. And you check whether 4 is less than 5 or less than 3 or greater than 3. 4 is obviously greater than 3. You move towards the right hand side. Then again you check whether 4 is equal to 4. Condition satisfied, you return the node. You said that element is false. So this is how searching happens. So this is how searching is made simply. Searching is simplified in binary search tree for you. Okay. So in next video we'll talk about sorting, and also we'll talk about traversers. Okay. So that's it about this class.